Hello, welcome to 2.7. We're talking about function operations. So we're going to take a quick jog back into your math history and way back to first grade. So in first grade, we said, hey, here's a bunch of things. These are called numbers. And numbers are 1 and 2 and 3 and 7 and 21 and 19 and all these different numbers in here. And then what we teach you is here's how to do some operations with them. We're going to add, subtract, we're going to multiply, we're going to divide. And then you progress on after that and you get into like third or fourth grade and we say, hey, these aren't all the things in math. We also have things, we call them fractions. And these are parts of numbers. So parts of whole numbers. So we go, hey, there's things like a half and 2/3 and 5 3/4 and all that kind of stuff. And then we teach you operations based on them. And this is kind of the progression of math. Then we might talk about decimals and equations and progress all the way up. Well, we find ourselves in that same place now. What we've been looking at are these group of things called functions. And it turns out these are all equations. F of x equals x squared plus 1 is an example. And now we're going to talk about operations of these things. Now here's the interesting thing about math though. As you get higher and higher in math, these are not the only 4 operations. In certain groupings of mathematical ideas, we have some operations don't occur, and then in some situations we have other operations, and that is what happens with functions. We do have addition, subtraction, multiplication, and division, but we also have another operation, and the symbol for it is an open circle. And what that is the operation of composition. So we're going to take a look at all of these operations today and how to do them with functions. So let's start with an example. We've got 2 functions here. This is f of x and g of x, and we're going to start by doing addition. The way you add functions, we're going to first of all talk about notation, how to write it. There's 2 ways to do that. You can say f of x plus g of x, or you can say f plus g of x. Both of these are correct and they mean the same thing. The way the operation works is not complicated. You just take one function and you add it to the next. And just like with numbers and fractions, addition is commutative, which means that you can write them in opposite order, and it's the same thing. So that's addition. Subtraction, the same notation occurs. You can write this, or you can write this. And the way that subtraction works is you take the first one and you subtract the second one. This is not commutative. Order matters, so the second thing being subtracted has to go second, just like with the real numbers. Multiplication. That is written as f of x times g of x, or f times g of x. Both of these notations are correct. You can use either one, and the operation is as you would hope it would be, just multiplying the 2 together. This is commutative. Order does not matter here, and you can flip these around just like you can with the real numbers. 5 times 3 is the same as 3 times 5. And lastly, division of the ones that we know already. We go f of x over g of x, or you can write f divided by g of x, means the same thing, and you take the put the top one on top and the bottom one on the bottom. Okay, now division is not commutative. Order matters. The top one has to be on the top. But a lot of times in functions, just like in fractions, when you do division, you create fractions on top of fractions. So if you'll see here, what we have is we have a fraction here, and really, because this is over 1, we have a fraction here. And this is not simplified. We're never going to leave fractions on top of fractions in this class. And so the way that you fix that, if you have a fraction on top of a fraction, is you take the bottom and you flip it over and you multiply. Why do we do that? Because if you remember when you learned how to divide fractions, which is what we're doing here, fractions, to divide, you flip and multiply, which is exactly what we're doing here. Then these cancel, and we are left then with just one fraction, which is 1 over 2x plus 3 times the square root of x minus 1. Whoops. And that is our final answer for division there. Okay, so those are the basic operations. And what I want to do is take a minute before we go on to composition, which is our 5th operation. I want to talk about domain. So domain, because what the homework problems are going to ask you to do is to perform the operation and state the domain of the function. Domain, as a review, is what x values are defined for the function. So, for example, just something from Algebra 1, you get something like a square root function that's shifted right 3. This is f of x equals the square root of x minus 3. That's the equation of this function. If you'll notice, this is not defined for all x values. I have x values over here that actually are not part of the function. I can't go up or down and hit the function. What that looks like algebraically is I cannot take -2 and plug it in here because I get the square root of -5, and that is an imaginary number. So the domain on this function is restricted. And the question is, how do I know when there's a restriction, and how do I know when there's not? So there are a couple situations that are most common here. This is not a comprehensive list, but domain issues occur when you have roots, as we've seen above, and when you have fractions, and when you have logarithms, which we'll talk about in a couple chapters. Now, there are also domain issues with trig functions. Trig is what we will talk about in the second half of the semester. I'm not going to address that now. We'll do that later. But no, there are other issues. But these are the most common in pre-calculus and for the most part of calculus. So this is where we're going to land. Roots, if you understand what was happening up here algebraically, you can't root a negative number. So the game plan for figuring out the domain, this is for domain, we're not solving anything or anything like that, is that you take the inside of the root and you say that has to be greater than or equal to 0. Now why? Because greater than 0 in math land means positive. So we're saying the inside of the root has to be positive. And in addition, it's okay if it's 0. 0 is okay. That's what that's saying, because the square root of 0 is 0. So an example, if I have f of x equals the square root of x minus 3, and I want to know the domain, sorry, I'm running out of room here, hold on. Then I take the inside, to calculate the domain, I take the inside of the root, which is just this x minus 3 part, and make it greater than or equal to 0 and solve it. So this is saying that x has to be greater than or equal to, typo, greater than or equal to 3. Okay? And that's your domain. Now, if you understand how the graphing works, this answer will make sense. You look at this function, you say, oh, this is shifted right 3, so the function's defined from 3 on up. So that's x is greater than 3. If we write it in interval notation, that'll be square bracket on 3 to infinity, which is how I'd like you to write it. So let's actually square that solution right there. Okay, another issue is fractions. Fractions have problems when the denominator is equal to 0. So your plan for figuring out a domain of a fraction is you set your denominator not equal to 0, because what we're saying is the denominator can't be 0, and we're finding the x value that makes that happen. So for example, if you have f of x equals 3 over x plus 2, I'm going to take the denominator, x plus 2, and say that can't equal 0. So that means x can't equal negative 2. Now, in this first example with roots, what the solution is telling you is what x can be. In this situation, what we're finding is what x can't be. So you need to kind of keep that straight in your mind. So what this is saying is x can be anything but negative 2. So if we're going to write the domain in interval notation, that means I can go negative infinity to all the way up to negative 2, but not 2. And a negative 2 all the way up to infinity. And that's the domain of a fraction. All right, and then the last one is logarithms. Now, we haven't studied those yet, so we'll come back to this when we're in the logarithmic section and review this again. But logarithms are similar to roots in that when you're taking the log of something, you cannot log a negative or 0. So the plan for logarithms is you're going to take the inside of what you're logging and make it strictly greater than 0. So what you're saying is, hey, this has to be positive and 0 is not okay. So an example is if we have f of x equals the log of x plus 4, then I take that stuff inside the log and make it strictly greater than 0. So x is going to be greater than negative 4, or in interval notation, negative 4 up to infinity. And this is the domain. Okay, now don't worry about number 3 as much right now. We're going to probably live in this roots and fractions in this section, but I wanted to show you all of those together in one place. So now let's scroll up to our operations and let's take a look at the domain. I'm going to do the domain on all of these problems in red. Okay, so let's first look at addition. I take this and I'm going to say, are there fractions or roots? That's always going to be the question that you ask first. Are there fractions or are there roots? And later in the course we'll be asking about logarithms too. So I look at my answer right here and I say, well, I've got fractions and I've got roots. So I need to address both problems that those create. So my first step, I'm going to take care of the fractions first. The plan with fractions is you take your denominator out and you make it not equal to 0. So you're going to solve this. X does not equal negative 3/2. So negative 3/2 is not a value in the domain. In addition, I need to deal with the root. The plan for roots is you take the quantity out of the root and make it greater than or equal to 0. So that means that x is greater than or equal to 1. Now both of these have to be true for the domain. So if you draw a number line and look at it there, here's negative 3/2 and here's 1. So this says that x has to be greater than or equal to 1, which is anything above 1, and it also can't equal negative 3/2. Well, negative 3/2 was already invalidated by this greater than or equal to 1, so it's kind of redundant. If I just say x is greater than or equal to 1, I take care of the problem at negative 3/2. So the domain then is going to just be x is greater than or equal to 1, or in interval notation, that's square bracket 1 to infinity. And that's your domain. Okay, and you do a similar process on all of these operations. So subtraction, look at, we've got the same situation. So the domain on this is going to be the same. The work's going to look the same, and the outcome's going to be the same. Multiplication as well. I've got still this same fraction and this same root, so my domain is going to be 1 to infinity. So kind of when you do the first one, the top three follow. Division can be different, okay? And you have to take a look at it a little bit separately. So for sure, we still have that x minus 1 has to be greater than or equal to 0 because we've got that root. But look at what's happening on the denominator. I've got two things on the denominator. The way that the denominator is going to be equal to 0, because it's factored, is that x can't equal negative 3/2, but also x can't equal 1. Because if I plug 1 into this root, I get the square root of 0, which is 0, and that zeroes out my denominator. So because in division, extra things get put on the denominator, sometimes you have more restrictions on your domain. So let's draw a number line of this situation. I'm saying that here's 1, and this guy is saying, well, I can be 1 and everywhere above. But the denominator is saying, hey, no negative 3/2 and also no 1. So now my domain is going to be 1 to infinity round bracket because I can't include 1 in that domain. All right, so that's how you do domain for all the four operations that you've seen before. Now let's take a look at composition. So we're going to do, I'm going to start with a simpler function. G of x is going to be, let's do the square root of x minus 4, okay? And I want you to find f. There's two ways to write composition. This is the operation. You can write f of g of x, or you can write f open hole g of x. These mean the same thing. I prefer this notation because this actually tells you what to do. Okay, let's review before we go through. You remember in Algebra 2, I said, hey, what's f of 3? And you'd say, oh, what that means is you plug 3 into the function, right? It'd be like this. And in previous sections, we've done f of, x plus h, which means I'm going to plug x plus h into the function. So in essence, what is happening with this notation is whatever is inside here gets plugged into this spot. So composition is actually the same thing, only now I'm looking at what do I want to plug in? I want to plug in g of x. So the function g of x gets plugged in to f. So this is going to look like the square root of x minus 4 squared plus 2. Same idea. See the pattern? These all look the same. There's something plugged into that squared part. Now, a lot of times you can simplify this. When you're done, if you notice, this root and the squared will cancel. So I get x minus 4 plus 2, which simplifies to x minus 2. Now, domain with these functions is a little more complicated than just checking your answer. If you look here, our answer to this composition is x minus 2, and that doesn't have any fractions or roots. But the issue is that our beginning functions did. And so this g of x is not allowing certain x's to be plugged in, even though the answer seems okay with it. And the issue is that sometimes the problem gets canceled off, as it did here with the root and the squared. So the rule for domain with composition is you need to check your final answer for domain issues, and you need to check the function that was plugged in. So in our situation, because the question was asking for f of g of x, we need to check our final answer, and that's going to be x minus 2. There's no domain issues there. But we also need to check the function that was plugged in, which was g of x. And that function does have domain issues. So because it's a root, I'm taking it out and setting it greater than or equal to 0. So x is greater than or equal to 4. And so our domain then is going to be from 4 to infinity. So you need to, what I would do is I would make some note cards for this domain issue and make sure that you have down on a note card composition, domain for composition of functions, and that you remember that you have to check your final answer and the function that was plugged in. As well, I would make note cards for the operations and how to find the domains of roots and equations. Okay, let's try one more composition problem. We'll say f of x equals 1 over x plus 2, and g of x equals the square root of x minus 3. All right, let's say that we want to compute f of g of x. That means that we're going to take the g function and we're going to plug it in right here into this little spot where x is. Now, it doesn't mean we're going to tack it on the end. It means it actually replaces that x. So it's going to look like 1 over the square root of x minus 3 plus 2. So see how this spot right here gets replaced with the g function right there. And the form is still f of x. It's 1 over something plus 2. But that little spot gets changed out with the g. And this is probably it. This is simplified for us. So now let's take a look at the domain. I have to check two things, fractions and roots. So obviously I have a root, okay? Not only do I have a root in the function that I plugged in, but I also have a root in the final answer as well. So let's check that. Whoops. I'm going to take this x minus 3, make that greater than or equal to 0. And solve it. So x definitely has to be greater than or equal to 3. That's the first part of my domain. The second issue that I have is I have a fraction. So the way I deal with fractions is I take the denominator and I make it not equal to 0. And I solve this. So if I subtract over the 2, then I square both sides, and then I add the 3. So I get x can't equal 7. So let's take a look at that on a number line. Here's 3. I can have a 3 all the way up. And then this says that x also can't equal 7. So I have a hole in my domain right there at 7. So if I'm going to write that in interval notation, it's going to look like 3 to 7, round brackets, unioned with 7 to infinity. And that's the domain. Okay, interesting. So that's how you do composition. An interesting fact about composition, in addition to how it's performed, it is not commutative. Order matters. Let's take a look. What if I ask you for g of f of x? Well, what that means is now I'm going to take f here and plug it in to the g function for x. So now I've got the square root is taking the form, and the fraction is going on the inside there. Okay, so you can see that answer is very different than this one right here. And let's look at the domain really quickly. Two issues again, we have roots and fractions. So the roots, the whole thing's a root. So I'm going to take everything on the inside and make it greater than or equal to 0. Okay, now this is a bit of a harder problem. We've got a fraction with an inequality. And we talked about how to solve these in Algebra 2. When you've got an inequality with a rational function, the first step is to get all your fractions together and combine your fractions. So we need a common denominator on this. I'm going to multiply by x plus 2 and x plus 2. And that's going to give me 3x plus 6 on the top. And now I can add my fractions together. I'm getting a negative 3x, and a 1 minus 6 is a negative 5. All right, and then I get my critical points and I make a sign chart. So this is a negative 2. Negative 3x minus 5 equals 0 when x equals negative 5/3. So that's here. Okay, and we test points to see where is this greater than 0, or where is it positive. And if you take, let's take 5, for example, and plug that in, 5 and 5, that's going to be a negative over a positive, gives me a negative number. Okay, over here, I'm going to plug in negative 3, and that's going to give me, whoops, if I plug in negative 3 for x, that's going to give me 9 minus 5 is a positive number, and negative 3 plus 2 is a negative. So this is also going to give me a negative. And if you plug a number in here, you're going to have to use a fraction. This number right here is 1 2/3. So negative 9 2/3, which is really close. You got to get a decimal, and if you do that, this ends up being a positive value. Okay, I did that on my calculator, but I just did it quickly to save some time in the video. So where is this fraction going to be greater than 0? It's going to be in that little space between negative 2 and negative 5/3. Okay. The negative 2 gets a round bracket because it came from the denominator. The negative 5/3 gets a square bracket because it came from the numerator. So this is the restriction on the root. Now we need to look at the restriction on the fraction of this function. And the fraction's simpler. Just take your denominator out and make it not equal to 0. So x is not equal to negative 2. Okay, now x is already not equal to a negative 2 because it got excluded in the previous section, so that means that doesn't add any information, and we have that the domain is from negative 2 to negative 5/3. Okay, so I just wanted to show you with this example that it's the composition of functions is definitely not commutative. So order matters here, so be careful which one you're plugging into which. All right, lastly, you can compose more than one function. So let's say we've got f of x equals x squared, g of x equals x plus 2, and h of x equals, let's say, x squared plus 1. If I want to, I can ask you, what's f of g of h? Now, another way to write that is f open dot g open dot h of x. So remember, both of those notations mean the same thing. And this is one of the only places in math where you work right from left. So what's happening is you're taking the h and plugging it into the g. The h goes into the g. And then that answer goes into the f here. And if you just take it one step at a time, it's helpful. So let's first take h and plug it into g. So I'm going to take this h function here and plug it in here. So that is going to give me x squared plus 1 plus the 2. And that is then going to be plugged into f. So if we simplify that down, that means x squared plus 3 is being plugged into f. And f is just x squared. So that means I'm just going to take this and I'm going to square it. And this is fine. I don't expect you to multiply things out when there's nothing to combine with. So I would leave this as your final answer. If there was something else added on or under it to combine, then you'd want to multiply it out. But I don't want you to multiply it out just for multiplication's sake. Okay, domain on this. Well, look, my final answer doesn't have any roots or fractions, nor do any of the functions that I plugged in. So that means I have no issues, and the domain is negative infinity to positive infinity. And that's your answer for your domain. All right, try some of these, and I'll see you in class.